Hello students, welcome back to the statistics course. Today we're going to discuss a survey of probability concepts, and let's start with the learning objectives. So there are 7 learning objectives. First, we're going to define the terms probability, experiment, event, and outcome. We're going to learn about assigning probabilities using a classical, empirical, or subjective approach. We're also going to learn how to calculate probabilities using the rules of addition and rules of multiplication. We're going to also review a contingency table. This is something that you've seen in the previous lecture. We're going to dig deeper in today's lecture. We're going to calculate the probabilities using the Bayes theorem, and then we're going to determine the number of outcomes using principles of counting, such as permutation and combination. So let's start with the first concept of probability. So it's a value between 0 and 1 inclusive. It means 0 is included as a value and 1 is also included as a value. A probability represents the likelihood a particular event happens. So for example, you can say with confidence, with probability 1, there is a chance of rain in Florida this year. And you can also say with confidence that there is a 0 probability that our sun will disappear this year. But there are range of values of probability that you can think of. One example is that there is a 0.5 chance of a head in a single toss of a coin, and then there could be a 0.7 chance of an increase in federal taxes in this particular year. And so keep in mind that probability, the closer to 1, the more likely that an event will happen. So there's one question, as an exercise. Theorem conducted a survey to over 100 airport train passengers. Out of the 100 passengers, 72 stated that the train ride was convenient. So is 72 a probability? Well, the answer is no. In this case, 72 is just the number of passengers that stated the train ride was convenient. So if you look at 72 was from 100 passengers that was surveyed. So we can say that about 0.72 of the passengers mentioned that the train ride was convenient. So 0.7 probability mentioned that the train ride was convenient. So this is one way of calculating probabilities, and we'll learn more about how we can calculate probabilities in several slides. Okay, so let's talk about the next definitions. So the first one is experiment. So experiment is a process that leads to the occurrence of one and only one of several possible results. Okay, so for example, it could be a roll of a die. It could be counting the number of members of the board of directors for Fortune 500 companies who are over 60 years of age. So those are examples of an experiment. The second definition is an outcome. So an outcome is a particular result of an experiment. So for example, if you roll a die, then you could observe a number 1. You can observe a number 4, for example. And for the other experiment, an example of an outcome will be, there is no BOD for Fortune 500 companies that is over the age of 60, or there are 29 out of 500 Fortune companies with BOD over the age of 60. So those are examples of possible outcomes. Now, an event is a collection of one or more than one outcomes of an experiment. So for example, when you roll a die, you can observe even numbers. So for example, you observe either 2, 4, or 6. And so that's going to be an example of an event. For the second experiment, an example of an event includes more than 25 are over 60 years, or for example, fewer than 50 are over 60. So these are examples of experiment, outcome, and event. Okay, so let's go back to the questions on PT railing that we discussed several slides back. So PT Railing conducted a quick one-question survey to over 100 airport passengers. PT Railing asked whether the train ride from Soekarno-Hatta Airport to BNI Sudirman Station was convenient or not. So what is the experiment? Well, in this case, the experiment is choosing 100 airport train passengers in a random manner. What is one possible outcome? One possible outcome would be 60 passengers mentioned that the train ride was convenient, or 20 passengers mentioned that the train ride was convenient, and so on. What about a possible event? Well, a possible event includes fewer than 50 passengers mentioned that the train ride was convenient, or for example, more than 20 passengers mentioned that the train ride was convenient. So those are examples of an experiment, an outcome, and events. So let's talk about several definitions of probability. In particular, we'll start with the classical probability. So the classical definition of a probability applies when there are n equally likely outcomes to an experiment. So the probability of an event will be the ratio between the number of favorable outcomes and the total number of possible outcomes. So let's talk about some follow-up definitions. The first one is mutually exclusive. So the occurrence of one event means that none of the other events can occur at the same time. On the other hand, a collectively exhaustive means that at least one of the events must occur when an experiment is conducted. Okay, one example of a classical probability is that suppose what is the probability of getting a 2 spot when you roll a die? Well, the number of favorable outcome is only 1, so that's one 2 spot, and then there are 6 possible outcomes when you roll a die. So in that particular case, the probability of an event will be 2/6 or 1/3. Okay, so consider an experiment of rolling a 6-sided dice. What is the probability that an odd number appears? So the first one is you have to list the outcomes. So the outcomes are 1, 3, or 5, and the total possible outcomes are 6. So in this particular case, the probability is going to be 3/6 or just 1/2. Another example, consider an experiment of rolling two 6-sided dices, and what's the probability that the numbers in the 2 dices sum up to 6? Okay, so in this case, the possible outcomes are a bit more complex in the sense that you have 2 6-sided dices. So the total number of possible outcomes is actually 6 to the power of 2, or 36. So it's basically 6 times 6. And so you can think of the outcomes would be the first dice is a 1, the second dice is a 6, the first dice is a 2, and then the second dice is a 6, the first dice is a 3 and 6, and so on and so forth. So basically you're going to have 36 possible outcomes. And so we're going to look at the event that the numbers in the 2 dice sum up to 6. So basically you have 1 and 5, you also have 2 and 4, you have 3 and 3, you have 4 and 2, you have 5 and 1. So basically there are 5 favorable outcomes. So the probability that the numbers in the 2 dice sum up to 6 is going to be 5/36. Another example, a large company must hire a new president. The board of directors prepares a list of 5 candidates, all of whom are equally qualified. The 2 of these candidates are members of a minority group. So to avoid a bias in the selection, the company selected the president by lottery. So basically you're going to choose one president and you have 5 candidates, and 2 out of the 5 candidates are actually minority group. So what is the probability that a minority candidate is higher? So the probability is basically 2/5. Okay, since there are 2 minority candidates out of the 5 total candidates. The next definition is the empirical probability. The empirical definition occurs when the number of times an event happens is divided by the number of outcomes. So the probability of an event happening is the fraction of the time similar events happen in the past. So the formula to determine an empirical probability is the following. It is the ratio between the number of times the event occurs and the total number of observations. Okay, so Stephen Curry of the Golden State Warriors made 278 out of 302 free throws attempts during the 2017 and 2018 NBA season. Now, based on the empirical approach to probability, then the likelihood of him making the next free throw is going to be 278 out of 302 free throw. Okay, so which is 0.92, which is quite high for an NBA player. Okay, so let's talk about the law of large numbers. So basically, over a large number of trials, the empirical probability of an event will approach its true probability. So for example, if you toss a coin, multiple times, then perhaps the probability of observing a head is going to be about 0.6, or for example, it could be 0.4. However, if you do more trials, say for example, if you do 1,000 toss of a coin in a consistent manner, then you may approach the true probability of 0.5. Okay, and the last concept is the subjective probability. So the subjective concept of probability is the likelihood or the probability of a particular event happening that is assigned by an individual based on whatever information is available. So suppose that you and I are making a prediction on the weather, okay, just based on observations. So my subjective probability on the chance of rain could be different with your subjective probability on the chance of the rain. It really depends on what information is available to me, to myself, and what's the information available to you. So for example, if you think that, if you've seen the news in the past week, and then you've seen the weather applications, and you've read articles from the meteorology and then the weather station, then you may have more information about the probability of rain. However, if I don't read anything, or I don't get any information, and if I don't even look at the the sky as an information, then probably my subjective probability on the chance of rain will be quite bad. Okay, so another subjective probability includes the likelihood of New England Patriots will be in the Super Bowl next year, or estimating the likelihood of a US budget deficit will be reduced by half in the next 10 years. So of course, experts making subjective probability will be better than novice making a subjective probability, because they have more information. Again, it's going to be based on the information that you have. So again, there are two approaches of probability. The first one is the objective approach. The second one is the subjective approach. There are two objectives approach, the classical and the empirical. So the classical is going to be based on equally likely outcomes, while the empirical probability is going to be based on relative frequencies. Okay. All right. So let's get into examples of whether the following is a classical, empirical, or subjective. So football player scored 15 out of his last 20 penalties, and so the probability that he scores the next penalty is 0.75. Well, in this case, it's actually the empirical, because it's the number of attempts, or it's the number of success divided by the number of attempts. Okay. A 7-member committee of students is formed to study environmental issues. What is the likelihood that any of the 7 members is randomly chosen as the spokesperson? Well, in this case, it's going to be classical, because there is a equally likely outcomes of a particular member chosen as the spokesperson. And the last one, the probability of rapid eruption in the next 5 years is 0.90. So this perhaps can be categorized into a subjective probability, and the idea is that someone may have an information about historical events of a Marapi eruption, and then he can use that as an information to predict the probability of a Marapi eruption in the next 5 years. Now, let's talk about calculating probabilities. So there are going to be, calculating probabilities using the rules of addition. There's going to be a separate discussion on the calculation of probabilities using the rules of multiplication. So the rules of addition refer to the probability that any two or more than two events can occur. The special rule of addition is used when the events are mutually exclusive. So the probability of event A or event B is going to be the sum of the probability of event A and the probability of event B. And you have, suppose that you have three mutually exclusive events, then the probability of A, B, or C is going to be the probability of A plus the probability of B plus the probability of C. And so, the illustration of a mutually exclusive events is that the events A, B, and C do not overlap and so they're mutually exclusive. Okay, so this is an example. A machine fills plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct weight. But because of the variation in the size of the beans and other vegetables, a package might be underweight or overweight. So a check of the 4,000 packages filled in the past month revealed that there are three possible outcomes or three possible events. One, it is underweight, it is satisfactory, and then overweight. So it's going to be denoted as event A, B, and C. So here you can see that there were 100 packages underweight, there are 300 packages overweight, and 3,600 packages that are satisfactory. So in this particular case, we want to know what's the probability that a particular package will be either underweight or overweight. Well, basically this is just going to be the probability of event A or event C. So it's going to be the probability of A plus the probability of C, which is 0.025 plus 0.075, which is equal to 0.10. Okay, so the probability that a particular package will be either underweight or overweight is going to be 0.10. Now, another example. So the events A and B are mutually exclusive, and so suppose that the probability of event A is 0.30 and the probability of event B is 0.20. So what's the probability of either event A or B occurring? Well, it's just the probability of A plus the probability of B, which is 0.5. And what's the probability that neither A nor B will happen? Well, this is going to be a concept of complement. So the complement of A or B is just going to be 1 minus 0.50, 1 minus 0.50, which is 0.50. Okay. Now, since I mentioned the complement, then let's discuss the complement rule. So the complement rule is used to determine the probability of an event happening by subtracting the probability of an event that is not happening. So the probability of an event A is actually 1 minus the probability of not event A. And so in this particular case, what's the probability of getting an underweight or an overweight package? Well, the easiest one is actually to just take the complement out of the satisfactory package. And so in this particular case, it's the probability of not satisfactory, which is 1 minus the probability of satisfactory, which is 1 minus 0.9, which is equal to 0.10. Okay. Let's take a look at another example. So so you have a following employee classification: supervisors, maintenance, production, management, and secretarial. And what is the probability that the first person selected is either in management or a secretary? And so in this particular case, the events are mutually exclusive because if you're a supervisor, you cannot be in other positions. Okay. And so what is the probability that the first person selected is either in management or a secretary? Well, it's basically going to be the probability of being a management plus the probability of being in secretarial. And what about the probability of not in management? Well, the probability of not in management is just going to be 1 minus the probability of management. Okay, so that's how you would utilize the rule of complement. In the previous discussion, we looked at a case where the two or more than two events are mutually exclusive. Well, in this particular case, we're going to look at cases or events where they're not mutually exclusive. And so if you can see in the Venn diagram, there is event A, there is event B, and there is an intersection between event A and event B. And the intersection is going to be A and B. And so the general rules of addition in this particular case is going to be the following. So the probability of event A or event B is going to be the probability of A plus the probability of B minus the probability of A and B. Okay, so this goes into the next definition of joint probability. So joint probability is a probability that measures the likelihood two or more events will happen concurrently. Okay. Now let's take a look at an example. So a sample of 200 tourists in Florida shows 120 went to Disney, 100 went to Busch Gardens, and then 60 visited both. So the probability of those visiting Disney is going to be 120 divided by 200, which is 0.6. And the probability of visiting the Busch Garden is 100 divided by 200, which is 0.5. Now the probability of Disney and Busch is going to be 60 over 200, which is 0.3. So basically the probability of visiting either the Disney or the Busch Garden is going to be the probability of visiting Disney plus the probability of visiting Busch minus the probability of visiting Disney and Busch, which is 0.6 plus 0.50 minus 0.30, then which is 0.80. So the probability of a tourist in Florida visiting Disney or Busch Garden is going to be 0.8. Okay. So what is the probability that a card chosen at a random from a standard deck of cards will be either a queen or a diamond? So suppose you have a deck of cards with a total of 52 cards, then first you have to calculate the probability of a queen. So there are 4 possible queens. So the probability of choosing a queen is going to be 4 over 52. And what's the probability of choosing a diamond? The probability of choosing a diamond will be 13 out of 52. And so the probability of a queen and a diamond is going to be 1 over 52. And so the probability that it will either be a queen or a diamond is going to be the probability of the queen plus the probability of a diamond minus the probability of the queen and the diamond. Okay, now you can scribble it out and then figure out the eventual result, but the idea is there. Okay, now let's talk about the rule of multiplication. So the rules of multiplication are applied when 2 or more events occur simultaneously. The special rule of multiplication refers to events that are independent. So the occurrence of one event has no effect on the probability of the occurrence of another event. And so the probability of A and B is going to be equal to probability of A multiplied by the probability of B. So a survey by the American Automobile Association AAA revealed 60% of its members made airline reservations last year. 2 members are selected at random. What is the probability both made airline reservations last year? So we're going to look at the probability of R1 and R2, which is equal to the probability of R1 times probability of R2, which is equal to 0.6. times 0.6, which is 0.36. Okay. Now let's talk about the general rules of multiplication. So the general rule of multiplication refers to events that are not independent. So a conditional probability is the likelihood of an event will happen, given that another event has already happened. So the conditional probability is the probability of a particular event occurring, given another event has occurred. So in this particular example, the general rule of multiplication of probability of A and B is equal to the probability of A multiplied by the probability of B given A has occurred. Okay? So let's discuss an example of a general rule of multiplication. So a golfer has 12 golf shirts in his closet. Suppose 9 of these are white, and then the others, the 3, are blue. So he gets dressed in the dark, so he just grabs a shirt and then put it on. He plays golf 2 days in a row and does not return the shirts to the closet. What is the probability of both shirts are white? Well, in this particular case, the events are dependent. And so whatever you take in the first instance is going to affect whatever you take in the second instance. And so the probability that the first shirt is white and the second shirt is white is the following. It's the probability that the first shirt is white multiplied by the probability of the second shirt is white conditional on the first shirt is white. And so the probability that the first shirt is white is going to be 9 over 12. And the probability that the second shirt is white conditional on the first shirt is white is going to be 8 over 11. So it's going to be 9 over 12 multiplied by 8 over 11. So it's going to be 0.55. Okay. Another example, the board of directors of a smartphone company consists of 7 men and 4 women. So there are a total of 10 BOD. A 3-member search committee is to be chosen at random to conduct a nationwide search for a new president. What is the probability that all of the 3 search members will be women? Okay, so basically here you have 6 men and 4 women, a total of 10. And you want to count the probability, the probability that all 3 search members will be women. So it's going to be the probability that the first one is woman multiplied by the probability that the second one is woman conditional on the first one being woman, and then the probability that the third is a woman conditional on the first and the second to be women. So it's going to be 4 over 10 multiplied by 3 over 9 and then multiplied by 2 over 8. Okay, so that's going to be the probability that all of the 3 search members will be women. And what is the probability that all 3 members will be men? So it's basically going to be the probability that the first one is man multiplied by the probability of the second one is man conditional on the first one being man, and then the probability of the third one is man conditional on the first and the second being men. So it's going to be 6 over 10 multiplied by 5 over 9 and then multiplied by 4 over 8. So the contingency table is a table used to classify a sample of observations according to 2 or more identifiable categories or classes. So 150 adults were asked if they were older than 50 years of age and the number of Facebook accounts they use. The following table summarizes the results. So are you over 50 years of age? Yes or no? And then you also have the number of Facebook accounts. So you have 1, 0, 2 or more. And so you can have different questions. So for example, what is the probability that an individual is going to have 2 or more than 2 accounts? Okay, or you can have another questions. What is the probability that at least of finding an individual with at least 1 account? Okay, another one will be what is the probability that an individual has at least 1 account and it's over the age of 50. Okay, so those are examples of questions that we can ask using the tree diagrams. Now, a tree diagram is a visual that is helpful in organizing and calculating probabilities for problems with several stages. So each stage of the problem is represented by a branch of the tree. Okay, so here is a number of movies attended per month by age. So you have A1 as no movies at all in the past month, and then A2 is going to be 1 or 2 movies per month. A3 is going to be 3, 4, or 5 movies per month, and A4 is going to be 6 or more movies per month. And there are the age categories, B1, B2, and B3. B1 being less than 30, B2 being 30 up to 60, and B3 up to 60. 60 and over 60, my apology. And so here is going to be the example, and the next one is the tree diagram. So basically you have 3 different age groups, 30 years or younger, 30 up to 60 years old, and then 60 years old and older. And so for each age group, you're going to find the number of movies. And so for example, what is the probability that an individual between the age of 30 and 60 watched 1 or 2 movies? So basically it's going to be 225 divided by 500. That's the probability of 30 up to 60 years old multiplied by 1 or 2 movies, which is 100 over 225. And so the multiplication will yield 0.20. So the probability that an individual aged between 30 and 60 watches 1 or 2 movies per month is going to be 0.20. Okay. Another example is what is the probability that someone age 60 or older watches no movies at all. So it's going to be 175 divided by 500, which is the probability of 60 years old or older, multiplied by the probability of 0 movies, which is 10 over 175. And so the probability that someone age 60 years old or older watching no movies at all per month is going to be 0.02, which is quite small in this case. It means that the likelihood of finding that individual is going to be quite rare. Now the next concept is a very important concept. This is a method of revising a probability given that additional information is obtained. Okay, this is a very useful tool in updating probability given that you have more information. So for example, what is the probability of a football team winning given that they will win today? So that's another example of a Bayes using a Bayes theorem for a updating probability. Okay, so let's get into the details. So suppose that we have 2 mutually exclusive and collectively exhaustive events, then the Bayes theorem is the following. So the probability of events A1 occurring conditional on B is going to be the probability of A1 multiplied by the probability of B conditional on A1 divided by the probability of A1 times the probability of B conditional on A1 plus the probability of A2 times probability of B conditional of A2. So basically the prior probability is the initial probability based on the present level of information, and then the posterior probability is the revised probability based on that additional information. Okay, now suppose 5% of the population of women have a disease, and A1 represents the part of the population that has the disease, and A2 represents those who do not. Okay, so let B denote the test result that shows the disease is present. Okay, and so the probability of A1, which is having the disease, is 0.05. The probability of A2 is 0.95, which is the probability that individual does not have the disease. The probability of B, so having the disease, conditional on A1 is going to be 0.90, which is the probability of test showing individual has the disease and it's correct. And there is a probability of B conditional of A2. So it's the probability that the result shows a disease is present, although an individual does not have the disease. So this is basically the probability that the test will be incorrect. Okay, and so let's take a look at the following diagram. So you have event. So A1 has the disease, A2 does not have the disease. So the prior probability is going to be P of A1 is 0.5 and P of A2 is going to be 0.95. Now the conditional probability, so it's the probability of showing positive conditional of being A1 is 0.90, and then the probability of positive test conditional that an individual does not have the disease is 0.15. And so in this particular case, the joint probability P of A1 and B is going to be 0.45, and then the probability of A2 and B is going to be 0.1425. And so the probability of B, so the probability of B is going to be the probability of A1 and B plus the probability of A2 and B, which is 0.1875. And so let's take a look into the posterior probability. So the posterior probability is going to be the probability of A1 conditional on B, and then the probability of A2 conditional on B. Now, the probability of A1 conditional on B is just going to be the probability of A1 and B divided by the probability of B, which is 0.24. And then the probability of A2 conditional on B is going to be the probability of A2 and B divided by probability of B, which is 0.76. Okay. Now, a randomly selected individual is going to be tested, and the test result indicate that the disease is present. And what is the probability that the test is correct? And so basically this is the probability that an individual has the disease conditional that the test is correct. So it's going to be the probability of A multiplied by the probability of B conditional on A1 divided by the probability of B. And we know that the probability of B is going to be the probability of A1 times probability of B conditional of A1 times probability of A2 times multiplied by the probability of B conditional on A2. And so the probability of A1 multiplied by the probability of B conditional on A1 is just going to be the probability of A1 and B, which is going to be 0.045, and then the probability of B is going to be 0.1875, and it's going to be equal to 0.24. So your prior probability of an individual does not have the disease is going to be the probability of individual has the disease is 0.05, but since you have seen that individual test is correct, then the probability of that individual has the disease is now 0.24. Okay, so you have a prior probability of 0.05 that an individual has the disease. Now, given an additional information in the test is correct, then the probability of an individual has the disease is now 0.24, which is the posterior probability. Okay. So let's take a look at multiplication formulas. So the multiplication formula states that if there are n ways of doing one thing and then m ways of doing another thing, then there are m multiplied by n ways of doing both. And so the multiplication formula is the following. The total number of arrangement is just m multiplied by n. Now this could easily be extended for more than 2 events. So for example, you have 3 events of m, n, and o, then the total number of arrangements will be m multiplied by n multiplied by o. Okay. Now this is an example of a multiplication formula. So when the American Red Cross receives a blood donation, the blood is analyzed and then classified by group and RH factor. So there are 4 blood groups, A, B, AB, and O, and the RH factors could be positive or negative. Now, how many different blood types are there? Well, basically there are 4 blood groups and there are 2 RH factors. So you're going to have A, RH positive, RH negative, B, RH positive, RH negative, AB, RH positive, RH negative, and then O, RH positive, RH negative. And so basically there are going to be 4 times 2 blood types. So in total there are going to be 8 blood types. Now the tree diagram actually provides you with a nice visualization of this application of the multiplication formula. Now another way of counting is going to be the permutation formula. So a permutation is any arrangement of R objects selected from a single group of n possible objects. So the permutation formula is going to be denoted as n p of R, or n permutation R. So it's going to be n factorial divided by n minus R factorial. Okay. Now suppose that there are 3 electronic parts to be assembled, so n is equal to 3, and because all 3 are to be inserted into the plug-in component, so R is going to be 3. So 3 permutation 3 is going to be equal to 3 factorial, so 3 factorials will be 3 multiplied by 2 multiplied by 1 divided by n minus R. So n is 3, R is 3, so 3 minus 3 is 0, 0 factorial is 1. So that's something that you have to remember, that by definition 0 factorial is equal to 1. And so if you have 3 electronic parts to be assembled and there are 3 plug-in components, so basically there are going to be 6 possible arrangements. So ABC, BAC, CAB, ACB, BCA, and CBA. And here the order of the parts are going to be important. Okay? Now another counting formula useful in determining the total number of outcomes is combination. So a combination is an arrangement where the total order of the object is not going to be important. Now this is going to be different with permutation, because in the permutation the order of the object selected is going to be important. And so the way that you read a combination is the following. So n choose R. So it's going to be the ratio between the n factorial divided by R factorial multiplied by n minus R factorial. So the Grand 16 movie theater uses teams of 3 employees to work on the concession stand each evening. There are 7 employees available to work. And so again, there are 16 movie theaters and there are 7 employees available to work. Now, how many different teams can be scheduled? So this is actually how many different teams of 3 can be scheduled. So it's going to be 7 choose 3. So it's going to be 7 factorial divided by 3 factorial multiplied by 7 minus 3 factorial. So it's going to be 7 factorial divided by 3 factorial and 4 factorial. And so it's going to be 35. Okay. All right. So that's going to be a survey of probability concept. I'll see you in the next meetings where we'll talk about distribution. Thank you.